Alright, let's continue. Okay, let me open the table of content first. Alright, we are on chapter 26, concurrency and introduction. And the last time we take a look at the simulation, homework simulation. So let's open that. Chapter 26, the homework simulation here. Basically checking out, what is it called? Different thread interleaving, something like that. So let me open that. Oh, what is it called? If I remember correctly, the last time we take a look at this one, simple race. Oh, okay. Take a look at the simple race assembly, something like that. Intro, I think we add this one, and previously we learned about what is it called? About how changing the value of register px in here change how, what is it? How the value being stored in the address 2000 here. Let me show that, I guess. Okay, I kind of forgot what is the option here. Okay, this one. Excuse me. Okay, this is the program. Test B. Okay. Thread intro, simple race, and then what flag did I use previously? I think T for the thread. Right, the default thread is 2, but let's use 1 for now. And then, yeah, maybe let's try without the argument flag here, argument vector flag. So maybe something like this. Or maybe, oh right, I forgot about the trace, the memory trace and the register trace, I guess. Okay, the memory trace is 2000. Wait a minute. Memory trace is 2000, okay. Okay. I hope nothing go wrong again. Alright. So yeah, we have this what is it called? The memory trace 2000, because we specify the memory trace 2000 here, and then the register trace here. Yeah, for the register we have to register here px and ax. So let's put that. Basically we are tracking the, what is it called, the value change in this memory address, and also this register ax and px, something like that. So it is condition code. Should we use this? I'm not sure. But yeah, let's try the simple one. Okay, see, the value in register 2000 is changed from 0 to 3 because we have this one. Basically we move the immediate value or constant value, maybe something like that, to the address 2000 plus any value in px. But because the px value is 0, it's like we have what is it, 2000 plus 0, something like that. But if we change that, change the value of px here to, let's say, 1, for example, the value of address 2000 is not changed, has not changed, something like that. So that is something to keep in mind. Okay, and then if I need to change that, let me try remembering that. Okay, print some extra information. Trace condition, okay. So that make me wonder, can we do something like this? Can we do something like this? I am not sure. No, we cannot. We cannot do that, okay. Yeah, I'm kind of curious how we trace. Oh, okay. Only using number. So maybe not like this, but like this maybe. See, if we change the memory address to track that is 2001, we got these 3 value here. We change from 0 to 3, right? Okay, and then if we change this to 2, the px, what is it called, initial value to 2, the value in address 2001 still up, have not changed at all, something like this. So that is something to keep in mind. when we are tracking the memory address with this notation, I guess. Right, it is like what is it called, 2000 plus any value in the px, something like that. And then I want to try out using, what is it, the interrupt, I guess. The interrupt flag here, the default is 50 interrupt. As maybe instruction, the unit that use here. Well, let's find out. Interrupt 3 or maybe 2. Let's try that first with the thread 1 here. Okay, what about 3? Okay, oh yeah, maybe that is the, what is it called, the total instruction before interrupt, maybe something like that. This is 4. Okay, 1 2 3 4 5. What about 4? Okay, as expected, I guess. What about 6? Oh, okay. So as long as we haven't hit hard here, there is no interrupt. Okay. What about when the thread is 2? Oh, interesting. Wait, there is an interrupt. Okay. Okay, 1 2 3 4 5, and then this is the 6 instruction, I assume. 7 8 9 10. Okay, interesting. So either the instruction finish first, or well, maybe the next instruction that will be interrupt. Maybe. I'm still not sure yet. And this is kind of interesting. Okay, the value is 0. Oh, right, because we are on different thread. So we have context switch from thread 0 to thread 1. We save all the value, all the register value, something like that. I guess so. It becomes 0 again. Okay. And then we move the value from this address to register AX. Okay, and then add 1 to the value in the register AX, and then move the result back to this address. Okay, and then hard. Alright. If I use, let's say 3, maybe. Oh, mean, if I use 3, probably we will interrupt during this instruction. Third increment. Okay. Interrupt. Context switch. Oh, okay. So every time we interrupt, we do context switch. Okay. Right. We are doing this again. But then the problem is that the value is not synchronized, maybe something like that. So the value in this register have not changed, you could say. I mean, the expected behavior would be, what is it called? Would be 3 plus 1 from that 1, and then plus 1 again from, oh sorry, not from that 1, thread 0 plus 1 from thread 1. Maybe something like that. Okay. And it become what, 5 maybe? That is the problem here. The end result in the, what is it called? In the address 2002, because px is 2 here, right, instead of 0. So the value in this address is 4 instead of 5. Okay, that is, what is it called? The race condition, I guess, something like that. And that, yeah, that make me curious. If I didn't have this, for example, interrupt every 2 instruction. Okay, still a problem because instead of 2, right, we have 1 here. Now let's try this. So basically interrupt after we move the value back to this address 2000 plus px. Okay, after we move back here, right, we immediately move the new value in the address 2000 and then add that to 1, right, and then move back to the address 2000. So the end result is correct, that is 2 in this case. The value 0 plus 1, that 0 plus 1, that 1. Okay, and then we halt. So the halt here is, well, switching, I guess, but we already done the, what is it called, the critical section before the halt occurs, something like that. So we get the correct, what is it, the correct end result in the address 2000 plus px. Okay, something like that. Now let's take a look at the question, I guess. Next, examine a simple program, loop.s. First, just read and understand it. Then run it with this argument. Read and understand it. Okay, let's try to understand that. Loop.s, okay. Oh, there is a lot of trailing white space here. Yeah, this is my Vim setup, I guess. This symbol means there is a trailing white space. Okay, with this argument. Okay, subtract and then check if the value in tx equal to 0 or not, I assume. If it is greater than or equal to 0, right, we are looping here, going to the top. So I assume this, what is it called? This conditional will be false if the value in tx, value in register tx here is negative or less than 0, something like that. Okay, then run with this argument 1. Okay, the program assembly here I100. Oh, every 100 instruction we have interrupt. Okay, then we track or we trace the, what is it called, the register tx here. Okay, this specify a single thread, an interrupt every 100 instruction, right? This is what I'm confused previously. What kind of measurement unit we have? Is this every second, for example, or millisecond? And it turns out to be instruction. So how many instructions before we have interrupt? So yeah, something like that. How many instructions before we are interrupting the thread? Okay, and tracing of register tx here. What will tx be during the run? Use the desi flag to check your answer. The answer on the left shows the value of the register or memory value after the instruction on the right has run. Okay, keep in mind that the value on the left is the value after the instruction on the right has run. Okay, let's check that out. Okay, this one, no memory address here. tx, I don't think, okay, we need this argument or initial value for the register, and then interrupt every 100 instruction. Okay, let's do that without the compute flag first, I guess. And of course, don't forget to change this, the program path or the assembly file path, I guess. This way, okay, wait a minute. Let's check. Let we have this one. Value of tx. Okay. Every 100, Okay, we have this one, let's say. Tx. Right. I assume the initial value of tx is 0. So this will be -1 maybe. And then test that. Okay, -1. When we test this, right, I assume this will be false. The x not equal 0, right? If I remember correctly, the 0 flag will be 0, I guess. And then, yeah, I kind of forgot what flag will turn on when we do this. Yeah, maybe there's another flag. Okay. And then the thing is that this one would be false. Okay. And we finished the instruction here. Maybe something like this. Let's find out. Okay. Yeah. That is because the initial value is 0, so we immediately skip the condition here and going straight to the halt. Now let's try using the argument here, tx, I guess, and then let's use 1. So the value in register tx is not 0 but 1, something like this. See, the instruction a lot bigger than previously. Previously we only have 4 instructions here. Now we have more than that, because the initial value of tx is not 0, right? Let me okay, this is 0 and then this 1. Wait, I kind of forgot. Oh, if we specify using the -a flag, where is it? I think this one, -a flag, the initial value would be that value immediately. Okay, and then subtract, what is it called? Subtract 1 becomes 0, right? This is still 0, this is still 0, and because true equal to 0, and then subtract again, -1, right? Then this one also -1. This one is false. less than 0, right? And this one is negative 1. Let's see if this is correct. Okay, see, the initial value is 1 for register TX that we provide in the there's a there's a flag here, so we subtract that and then become 0. Test, we check whether the value in TX equals 0, something like that. And if I remember correctly, this test instruction using n bitwise n, if I remember correctly, something like this, and then check whether the result of the test is greater than or equal from the register flag. So there is this thing x86 R flag, if I remember correctly. Yeah, there is this flag register. To put the current, what is it called? To put the current state, maybe something like that. Let me copy this in the chat in case anyone wants to take a look. Okay, and then we subtract again the value in TX register, test again, and then false because it is less than 0, right? This one is true because again greater than or equal, so equal 0 is also considered there. So something to keep in mind. And then because this is false, we are not jumping to the label top here and going through the next instruction with is halt. Something to keep in mind. Okay, it's the test flag to check your answer. Okay, same code, different flag. Okay, alright, the same code or assembly instruction. And then okay, we are using 2 thread now instead of 1, and then the interrupt still 100 instruction every 100 instruction. And then this one, the argument for the register, this is, what is it called, the initial value for the X register for thread 1, and this is for thread 2, maybe something like that. And then we track the change in the TX register. Okay. We specify 2 threads and initialize each TX register to 3. Okay, what values will TX see? And we test it to check, does the presence of multiple threads affect your calculation? There are arrays in this code. Okay, let's check that out. Okay. Alright. have this one. Let me copy that. Okay, what is it again? Oh, 3, not 1, okay. Yeah. My pet. Okay. I think it's gonna be long, right? Okay. Alright, let me copy that here. Left. That messed up the indentation. Okay, maybe something like this. 3 and then subtract 1 become 2. This one still 2. Still 2. This one subtract again 1. Right. Test this. Still 1. Okay, subtract again become 0. 0. Okay. Subtract again become negative 1. Negative 1. And then half. Okay. Now switch to. Oh. Yeah, this is interesting. What is the value when we context switch here? I haven't noticed that. Okay. Interrupt. Oh, maybe the previous one. Maybe. Okay, let's assume it is the previous one. So it becomes something like this. And then when we subtract, oh, or maybe other than the previous one, is it gonna be the new register value? Maybe something like this. And then we subtract that, become 2. Subtract that, become 1. Okay. And then subtract that again, become 0. Subtract that again, become negative 1. And then half. Yeah, this is the thing that I'm not sure. When we context switch, is the register value immediately changed or not? Well, let's find out if my solution here correct or not. Okay. Alright, looks like when we switch, context switch here, we immediately change the value in the register TX to another context value, or in this case another thread value. Okay, but then I'm also curious about the interrupt here. Will the interrupt change the value immediately or not? Interesting. Okay. 3, okay, 2. Alright. Yeah. Looks like it is the same. Okay. The value in the px register, tx register here. Okay, and I'm kind of curious what happen if, let's say, we interrupt every, 6 instruction, maybe something like that. Okay, let's check that out. Okay, so when we interrupt, we also context switch, right? And the value in the register tx immediately switch to, okay, interrupt again. We are going back to this value. Okay. Alright. Does the presence of multiple thread affect your calculation? In this case, maybe not. Is there a race in this code? I mean, it depends, I guess, on the expectation. If we expect the value tx to, what is it called? To have the total, what is it called? To have the end result from the 2 thread, then maybe there is a race condition here. But then again, we already changed the initial value on the context switch, right? So I don't think that is the intention or the expected result. What is it? Are we expecting the value in register tx to hold the result from thread 0 and thread 1? If that is the case, then yeah, there is a race maybe, but then again, we already provide the different, what is it called? We already provide the initial value here. So maybe not. Maybe. Yeah, I'm still not sure. I mean, what race condition are we expecting here? I mean, from the previous one, the, what is it called? Simple race, if I remember. From the simple race, we have a race condition because we are saving the value in memory trace, so there's a shared resource, right? But then again, are we considering the register here as a shared resource? Are we considering register as a shared resource or only the memory? Like, for example, RAM or something like that. So if we consider register as a set resource, then yeah, there is a race condition. But if not, if we only consider the memory as the set resource, like the, what is it called? The simple race here, then yeah, no, the loop here doesn't have race condition, especially with this configuration, maybe something like that. Okay. Hello, this time. Welcome. Keep going. Good luck. Okay. Thank you. Okay, run this. Still the same. Oh, interrupt every 3. Okay. What is R? Lowercase r. Let me check. Oh, random interrupt. Interesting. So maybe instead of interrupt every 3 instruction, there is a chance that the interrupt will happen during during the first instruction, maybe something like that, after we execute one instruction, and then maybe 2 instruction, and maybe 3 instruction. So there is 3 possibility. 3 possibilities interrupt after execute one instruction, and then after 2 instruction plus 1 is 3 instruction with this random interrupt, I guess. This make the interrupt interval small or random. See, so we can have the interrupt less than 3 instruction. Use differentiate to see different interleaving. Does the interrupt frequency change anything? I'm not sure. Is it gonna change anything? Maybe not. You know what? Let's try this first, I guess. 3 instruction. Okay. Yeah, I'm kind of curious. I don't think it's gonna change anything. Right? I mean, again, it depends if we consider the register as shared memory as a shared resource too or not. The result is gonna be the same, that is -1 for each thread, right? But yeah, maybe it is more difficult to predict because the interrupt is random. Maybe something like that. Does the interrupt frequency change anything? It changed the, what is it called? does change something, but I'm not sure how to explain this. Okay, to answer this question, does the interrupt frequency change anything? In this case, yes. What kind of change it is? Right. It makes, what is it called? Maybe something like this. It holds the yeah, first of all, using the randomizer here makes predicting the interrupt hard, I guess. Maybe something like that. Make predicting when the interrupt happen will be harder, and also some instruction will be left, what is it called, hanging, maybe like something like that, more often than using the one without randomizer, random interrupt here. So for example, we are just testing this, right? And then suddenly we move to another thread to subtract the value in the register TX here. So there is that. Maybe. I mean, I'm trying to figure things out. But the end result is that, well, both threads have the negative 1 in the register TX. So yeah, it does change something, but I'm not sure what kind of change it is yet. Again, at a glance, it changes. What is it called? Compared to the previous one. And that is, yeah, wait, comparing that to the previous one, this one, right, with the interrupt every 100, what is it, every 100 instruction, see, compared to that, we keep switching back and forth between two threads instead of waiting one thread to finish and then switch to the next thread. Maybe that is the big difference compared to using interrupt every 100 instruction, and then this one using 3 instruction and randomize that. Maybe using seed, let's try that. Oh, okay, interesting. there is some difference for sure, but I am not sure what kind of effect will make this. Again. The end result for both thread 0 and 1 is gonna be -1, right? So yeah, I'm not sure about this one. Does the interfrequency change anything? Well, the interfrequency change about how we switch from thread 1 to thread 2. That is the biggest change, I guess. But I'm not sure if there's any major change, especially in this scenario. If it is in the simple, what is it called? Simple race scenario here, the change might be more significant because we have the shared resource in the memory, right? But in this case, we don't have that in the loop assembly here. We don't have that set memory space unless we consider, what is it called? The TX register are a shared resource. So there is that. Yeah, other than how the program switching between thread 0 and thread 1, I'm not sure if there is any major change in this scenario at least. Okay. Now a different program, looping rest no log. Okay, you know what? Let's try this question 4 on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.